All right, guys, so we're going to continue graphing our sine and cosine curves here, and then we'll just get into some of the transformations on this. So let's go back and review some of the basic transformations and see how they apply in basically the same exact way as they did with any function, okay? So let's take a look. So as a little review, or kind of like a warm-up, if we think back about the parent function for the absolute value of x, okay, and we know that one, or we hopefully should know, that one just kind of looks like a v centered at the origin here. This is just the parent function here, y equals the absolute value of x. Okay, so each of these transformations, each of these little adjustments to the equation transforms or changes that original graph a little bit. And what I want to focus on, remember, is anytime you have a plus or minus, okay, that's going to be a shift. And if the plus or minus occurs inside the function, okay, and inside the function for this example means inside the absolute value bars, because that's where the x is, it's going to be a horizontal shift. And those always occur, or they always take place in the opposite direction. So a plus 1 is actually going to shift the graph to the left 1 unit. Okay, so this thing would end up shifting to the left and kind of look something like that. Okay, same shape, same everything. The plus 1 on the outside in part B, anything on the outside is affecting y values, so that would be a vertical shift. And those do go in the direction that they should go, right? So this one would shift the graph up 1 unit. It would shift the original red graph there just up 1 unit. Okay, the other type of transformations are done from multiplication. Okay, so same thing, you can have multiplication going on outside the function or inside the function, and the same rules apply. Outside the function is going to be a vertical change, and this time it's going to actually stretch the graph, okay, because we're multiplying by something larger than 1. It's going to vertically stretch. All the y values would end up getting to be twice as tall, so it would actually kind of look like this. It would be stretched up vertically. Okay, and the other case, multiplying by something on the inside, again, it's going to be a horizontal, but this one, again, remember, is the opposite. It's kind of the inverse, so multiplying by 3 is actually going to shrink the graph inward. So it would actually, let's see if I can pick a different color, it would take the original red graph and all the points would come in. Let me see if I can draw that a little better. So the original parent function, like this, would actually end up coming in closer. So because the points came in horizontally. So it's kind of the same end result as a vertical stretch for this function, but really what it's doing is a horizontal stretch or shrink, okay? And we're going to see when we do these sine and cosine, these trig functions, it changes the period, because the period is the horizontal distance it takes to do one cycle. Okay, so let's take a look at a couple examples. That was just a little review and a little refresher for you. Okay, so here's a graph that I had made on Desmos. You can see the dotted black graph there is just your regular old cosine graph. If you notice, it starts out when the angle is 0. Remember where these come from here again. So cosine, when you're at 0 degrees, the cosine is following the x-coordinates of the unit circle, basically. So that's why it kind of starts out up here. And then by the time you get to pi over 2, it is back to a x-coordinate of 0. Over here at pi, the cosine of pi is -1 because that's the x-coordinate way out here. We get down to 3 pi over 2, we're back to 0, and then it ends up coming back to where it started. Okay, so that's a regular old parent function of the cosine, then it would continue and go on and on and on forever in both directions. Okay, what ended up happening, this is an example of what's called a period change. Okay, it's a horizontal stretch or shrink. Okay, we're multiplying by 2 on the inside there. Okay, that was supposed to be parentheses. Let's use a marker and do that. The inside function, the function is cosine of x. So in this case, we were taking the cosine of 2 times x. Okay, that's a horizontal shrink. And what you notice happened, it took this, the dotted black line, and notice how it kind of like shrunk it in. Okay, what really happened, each of these points got compressed in, okay, like that. And it ends up kind of making the graph do cycles. It does a full cycle right there, right? So where that was only half of the cycle of the original cosine graph. This thing is now doing 2 full cycles in that time period. Okay, and that's the way of horizontally compressing these things. So what we're going to do when we graph these, sometimes it's easier to just graph one cycle. So the one cycle of the cosine of 2x graph would occur from here to here. Okay, so we're just going to kind of draw that portion of it, and we're just going to change the scale along the x-axis. So let's take a look at what I'm talking about. Let's see, how would we graph one of these on our own? Graph here too. This was one cycle. Okay, it only took pi units along the x-axis. So what we're going to do, when we pattern is what we did here, but what we just graphed was just this one portion of the grid. Okay, so let's talk about, again, cosine of 2x. Okay, my advice is to first step on these is to set up the scale on the x-axis. Okay, and what we got to think about, the normal period of a graph is 2 pi, because that's a full circle. Okay, this thing, because of this 2 right here, is being compressed. So the period, little formula you can always use, will be 2 pi is the normal period. Since it's 2 times x here, remember it's always the inverse, so we're actually going to divide by whatever that value is. Okay, 2 pi divided by 2 is just pi. Okay, so what that means for us, let me take you back to these. We're still going to use the 4 little intervals or whatever, but instead of keeping them the usual pi over 2, pi, 3 pi over 2, and 2 pi, when the period has changed, like it has in this one, we're just going to make this last graph here be whatever the period is. Okay, that way I'm just going to follow the same pattern as graphing a regular cosine curve. We just kind of almost cheated in a way, and we're just going to graph it but on a different scale. So we can still follow the same pattern we graphed before, we just change the scale on it. Okay, so what that means for us is if that's pi, the second interval is halfway there, so that's pi over 2. Okay, the next one is half of that, so pi over 4. So each grid mark is pi over 4, so it's 1 pi over 4, 2 pi over 4. This would then be 3 pi over 4, and the fourth one is pi. Okay, and the reason that's going to help us is because now all I have to do is sketch my normal cosine curve, okay, which we know cosine, again, if you just want to think about visually, where does it start out? It starts out, the x coordinate out there is 1, okay, so the cosine is going to start here. By the time we get up to here, it's going to be back to 0, then down to -1, back to 1, or I'm sorry, back to 0, and then back up to 1. And it's going to end up doing this kind of thing where it's going to keep going, okay? And all we did, we just changed the scale to fit the correct period, okay? It was the same. Now this one, as far as amplitude and midline, none of that changed, okay? There were no transformations, right? This was just the only change, the only transformation was changing the period. So the amplitude is still 1, because again, that's the height from your midline. The midline on this example right here is still through y equals 0. We didn't have any shifts, okay? And the amplitude measures the height from the midline of 1 unit, and that's that. Okay, let's look at another example. All right, 2 times the sine of x over 3. Okay, this could be written if we wanted to as 2 times the sine of 1/3 x. Okay, that's the same as x over 3. Okay, because what I want to do in this case is I always want to find that period first, and the period is the thing that's tied into the horizontal stretching or shrinking. So the little formula we saw on the last page, the period will always be 2 pi divided by whatever this multiple is. We'll see, we're going to name that b. As we add on this, the multiplier on the outside will be a, and the multiplier on the inside will be b. Okay, and then there'll be shifts and stuff later. But whatever that b value is, in this case is 1/3. You can always get the period by taking the standard period of 2 pi and dividing it by b. So we're dividing by 1/3. And remember, when you divide by a fraction, that's the same as multiplying by the reciprocal, so it's really like multiplying by 3. So the 2 pi will actually become 6 pi. Okay, so we're going to set up our scale. Okay, let's see if I'm going to zoom in so I can write this a little more neatly. The 6 pi will be the fourth one out here because that is the last one. It's always 4 intervals. So this would be 3 pi. That's half of it, right? Half of 3 pi is 3 pi over 2. Okay, and then if we want to just get that middle one, so if it's 3 pi over 2, 6 pi over 2, it would then be 9 pi over 2, because each box is 3 pi over 2. So just to get the whole scale labeled, I decided to put that on there. Okay, and then all we need to do now is fit in a normal sine pattern into that scale, and then that will have taken care of the period change. Okay, so a normal sine graph, okay, starts out here. Sine is going to be the y-coordinate, so it's going to be starting at 0. Okay, at the first checkpoint it would be up at 1. Now this one actually has an amplitude of 2 though, okay, because remember the parent function would be there, but we're multiplying by 2. I'm just going to take care of that at the same step. Okay, that's 2. The next checkpoint we're back at 0. The next checkpoint we're down at our minimum, but again this time it's going to be -2 instead of just -1. And then we're back to our midline again. So here's our graph. Okay, it does keep going. Both directions. Remember, this thing repeats over and over and over. Okay, so in this case, our amplitude, we're going to see the amplitude will always be that A value out front here. Whatever you multiply, that's going to end up being your amplitude. Okay, and then finally for this one, the midline. If we see the midline here, okay, it's still at y equals 0. We're going to see shortly here the midline will only change if there's a vertical shift on the outside. You know, a plus or minus out there will shift the midline up or down. Otherwise, it's going to be going through a midline of 0. Okay, so here's a little summary page of that again. You'll have y equals, and then the outside multiplier, the vertical stretch ends up becoming the amplitude of the graph. So don't think of these as all brand new things, right? Amplitude is really just the vertical stretch, okay, multiplying on the outside. Then it could be a sine or a cosine, or it could be any function actually. And then the b times the theta, sometimes that'll be in parentheses, sometimes not. That b value is going to be your horizontal stretch factor. And what it does in these graphs is it impacts the period, okay? Because again, that's the horizontal distance it takes to complete one cycle. Now we're going to be sticking a lot more with radians. It could be 360 divided by b to get the period, but again, all these graphs generally use the radian, 2 pi over b. One other note then, if we just think of this equation, jot this down here, that the period equals 2 pi over b, just by doing a little bit of algebra, okay, we could multiply both sides by b and get b times the period equals 2 pi, which then implies if we divide both sides by the period, that b will always equal 2 pi over whatever the period is. Okay, and that's just what's shown right here. So let's say, for example, we're going to do one in a second where you're going to know the period. Okay, like if I give you the graph, you'll know the period. You can use that to find the value for b. Okay, so let's take a look. Let's do an example where they give you a graph and we want to come up with the equation. Okay, here's an example. Here's a nice looking graph here. Let's see if we can piece this together. Okay, so first off, is it a sine or is it a cosine? Okay, and honestly, if you're real good with your transformations and shifting and stuff, it could be done either way. Okay, we'll get into more of that later. But to me, the key indicator for this one is since it's starting at the origin, it's starting at its midline. Okay, I can see the maximum's 2, the minimum's -2. So the midline right here is y equals 0. Okay, when a graph starts at its midline, if you think about the unit circle again, the one that starts at its midline is the sine graph, okay? Because we're looking at y coordinates for sine, right? It's starting at 0, then it goes up like this one does, then it comes back to its midline, then it reaches its minimum before coming back to start, okay? So sine curves are the ones that start at their midline, okay? Now, let's think about the period and the amplitude and all that good stuff. So we know it's a y equals something sine of something, right? Okay, so the amplitude, which is going to go in front and be the vertical multiplier, vertical stretch, from the midline, this thing's going up 2 and down 2, so that is the amplitude. Okay, so all we need to find now is the period, and that'll give us the b value. Okay, so the period of this graph, okay, how long does it take to do one cycle? Okay, let's highlight a cycle here. So we're starting here, the cycle is maximum, back to midline, and minimum, back to midline. Okay, that's where it's going to start to repeat and do the same thing again. Okay, remember at the beginning of the section they had you draw the rectangle around the one cycle. Okay, they would look like that, right? Boom, there's one cycle. So the period of this is 120. Okay, maybe it's days or weeks or something. Okay, that means that there's a phase shift, or I'm sorry, there's a period change here. That period is not 2 pi. Okay, so there's going to be some multiplier on the x to horizontally stretch or shrink this thing. The 120 does not go in the equation. The b value does. Okay, our equation is going to be y equals a times sine of bx. Okay, we know a is 2. We're trying to now find b. It's not 120. Remember, the b value is the period. Related to the period, it is 2 pi over the period. Okay, we found the period on the graph to be 120. 2 pi over 120 reduces to pi over 60. Okay, that's what's going in our equation. Pi over 60 is the multiplier on the x value. Okay, that's the b value. That would make the period be the 120 that it needs to be, as this graph shows. All right, and the last thing we can do on these is just include shifts. Okay, so basically you're going to set up the period first, then get the function graphed using the amplitude like we just did on the previous examples. But then there can also be some shifts. Okay, so let's take a look at this one. This one, it's actually a little bit tricky how they wrote this. And the deal is basically you want to have the shifts. Okay, let me see if I can write this out here. The whole deal with all the transformations is, if it's, let's say this one's y equals a, some a value times cosine of b, x minus h plus k. Okay, and let's talk specifically about these. We talked about how the a is the amplitude, right? We've done that. Okay, the b value is used to get the period, because the period is 2 pi over b. Okay, we've been doing that. Okay, the only other new things, and they're not even really new, we just haven't done them with these yet, are the transformations. Horizontal shift, right? Adding or subtracting inside the function. Oh, why is that moving all over the place? And the k on the outside, of course, is vertical shift. Okay, adding or subtracting on the outside. So let's put it all together. And the reason this one's slightly tricky, okay, is because first off, here's our a value. That's our amplitude. This 3 is the b. But the way the 3 is written, it's not where it needs to be. Notice how the 3, the b, should be in front of parentheses. What I'm getting at is this plus pi is not the horizontal shift. Okay, we need to factor that 3 out. And sometimes it's written this way and sometimes it's not. But this correctly should be written as with a 3 out front, factored out. So if we divide the 3 out of the x, it becomes just x. And if we divide the 3 out of the pi, it would need to become pi over 3. Okay, so I factored out that 3 right here to get it in the correct spot, because the shift on this one, the horizontal shift, is really pi over 3, not pi. Okay, but everything else is kind of set up the way it needs to be. Okay, so just watch that now. Sometimes it's not, you don't have to worry about that. Sometimes the b value is already factored out. All right, so let's think about this. My first step to you guys is still set up the period. Set up the x scale. Okay, like we did before. This one, having that b value of 3, okay, means that the period will equal always 2 pi over b, so 2 pi over 3. Okay, so let's set that up. 1, 2, 3, 4. Let's zoom in so we can write these neatly. This last one is going to be our 2 pi over 3 because that's what the period is. Okay, so that means the second tick mark is half of that, so it's 1 pi over 3. Okay, half of pi over 3 is pi over 6. Right, because you can double the denominator. So if we count these out to get that missing one, it's 1 pi over 6, 2 pi over 6, then 3 pi over 6, which is the same as pi over 2. Okay, so each x grid is pi over 6. We have our scale set up now. And let's think about what this graph looks like. Okay, let's graph everything except the shifts. Okay, let's just graph it as y equals 2 cosine of 3x. And then all we'll have to do is apply this shift and we will be done. Okay, so the 2 cosine of 3x, I'm going to do this like in yellow just because it's not our final answer yet, but it would start up at 2. Cosines go down, down, up, up, right? So it's going to do something like this. Okay, we got our scale set up. That is the graph of 2 times the cosine of 3x in yellow there. Okay, I'm using that as a guide. Okay, because what I need to do now is our last step is to take care of this transformation, which since it's on the inside as a plus, it means we are going to go to the left pi over 3. So I'm just going to take each point and I'm going to slide it, or shift two boxes, because pi over 3, if you look at our scale here, is 2 boxes. So if I take this point, it's going to go 2 boxes to the left. Okay, if I take this point, it's going to go 2 grids to the left. This point, 2 grids to the left is there. This next point, 2 grids to the left is now there. Okay, this maximum up here, 2 boxes to the left is there. Okay, so this graph actually does this kind of thing. Okay, the red one is our actual final answer. Okay, I used the yellow one to get us, get us a guide, and now the red one is going to be the final answer that we want. Okay, so just follow the same steps. I really suggest setting up that X scale first, graphing everything. Use your 4 points like we've been doing, and then take care of any shifts. Okay, so let's do one last one together. Okay, here's one. Y equals 2 times the sine of x plus pi over 2 plus 1. Okay, so let's think about what we got going on here. So first, step 1, set up the x scale. Okay, every single time. I just find this makes it so much easier. Okay, now this one, remember it's a times sine. This one doesn't have a b value. Okay, so we don't have to worry about any period change. Okay, there's no horizontal stretch or shrink on this one. We do have an amplitude change, and then we do have a horizontal shift and a vertical shift, okay, and an amplitude. So it's going to be a normal standard scale, okay? Our standard scale without any shifting is the regular old period of 2 pi. So 1, 2, 3, 4, this is 2 pi, this is pi over 2, and 3 pi over 2. This is standard parent function scale, okay? Because there's no transformation on the horizontal stretch. So all I want to do, let's do it in yellow again, or we'll do yellow. I'm going to graph it without the shifts. I'm just going to graph y equals 2 sine of x, okay? And use that as a guideline, okay? 2 times the sine of x. We need to know sine starts at 0, goes to its maximum, which in this case is 2 because the amplitude, then minimum, then back to midline, then minimum, back to midline. Okay, this is the graph, okay, of 2 times the sine of x. Now what we need though is just to apply the 2 transformations. And I'm going to do them at the same time. I need to take each point to the left pi over 2, and then also up 1. Okay, now this is nice. So when we go left pi over 2, that's 1 box. Okay, based on our scale, that's why it's important to know the scale. Left pi over 2 is just one box. Okay, So let's take our 5 points and move them. Okay, so this point right here, one box to the left and up one would end up there. Okay, this point, one box to the left and up one would end up there. Okay, and then moving the other points, this box, one to the left and up one. This one to the left and up one. This one to the left and up one. So our final ends up doing something just like that. And just to finalize the properties here, so we're clear with all these terms and whatnot. Again, the amplitude is just going to be your vertical stretch. Okay, we'll see it's 2. Period on this one, it had no change from the standard, right? There was no b value, so the period is the standard 2 pi. Now this one did have a midline. If we take a look, let's do the midline. The midline on this one was right here. Okay, that was the points it kept going through at its midpoint. The midline will always be whatever the vertical shift is, okay, because the typical midline was through 0. If you look at the yellow dotted graph, its midline was through y equals 0. This had that vertical shift to move that up 1 unit. Okay, so one last real quick summary page. Again, you have y equals a times, and then it could be whatever function you want, b times x minus h plus k. Okay, what each of these things mean, again, it's not new, it's just kind of in a new context. The vertical stretch here is going to end up becoming the amplitude of the graph. Okay, the b value, that's what you're taking the sine or cosine of. B is a multiplier inside, so it's a horizontal stretch or shrink, and what that changes in this problem, or these problems, is the period. Okay, so you're going to always find the period by taking the standard 2 pi and dividing it by whatever b is. And that's the step I usually do first, and then set your scale up, and on the 4th one, you're going to put whatever the period is, because that's when it'll do its full cycle. It's always based on the 4 little checkpoints, I like to call them. And then the final 2 transformations are just your horizontal and vertical shifting. Okay, and if you do it in that order, you can kind of do this stuff by hand instead of relying on technology. Sometimes it's harder on technology to just get things accurate and answer questions that we're going to have to be answering. So you really want to know how to set these up kind of manually. Okay, so hopefully that helps.